So far we've been talking about integrals that are proper. The integral from a to b of f of x dx. What makes them proper is that a and b are numbers and f of x is a continuous function. To use the fundamental theorem of calculus, we know that f of x has to be continuous because when we were doing a proof, we used the mean value theorem on the antiderivative of the function little f of x, meaning that that antiderivative function had to be differentiable. Therefore, f of x itself has to be continuous. Also, when we were doing the proof, we worked with a and b as if they were numbers. So today, we're going to talk about improper integrals. So first of all, what if one of a or b, or both of them, were infinity? So what if you were trying to find, on this pink curve, y equals 1 over x, what if we were trying to find the area from 1 all the way to infinity? We want all that area under there. In order to do that, we still are going to have to add up an infinite number of small rectangles. So we still would like to use an integral, a definite integral. So the way we're going to do it is to take the integral from 1 to infinity of 1 over x dx. This is improper. Infinity is not a number. The way we're going to get around that is to go the integral from 1 to t of 1 over x dx, where t is representing a number, and then we're going to, at the very end, take the limit as t approaches infinity. So, think about what you believe the area is going to be under this curve, between the curve and the x-axis. And then, now we'll actually work it out. So the antiderivative of 1 over x dx is the natural log of the absolute value of x, but we don't have to worry about absolute value because we're going numbers bigger than 1. So if we plug in, we get the natural log of t minus the natural log of 1, which is 0. So we just have to say, what does the natural log function do as t approaches infinity? Well, it goes slowly, but it keeps growing. It goes all the way to infinity. So we would say that the integral diverges. It diverges to infinity. So, and the area, the amount of area, is an infinite amount of area, more than we could possibly imagine. And that might have gone along with your intuition. Well, what if we switched to this blue curve, y equals 1 over x squared? It looks like there's going to be less area, but is it still going to be an infinite amount? Let's find out. What's the integral from 1 to infinity of 1 over x squared? Again, it's improper, so we take the integral from 1 to t of 1 over x squared, which we might as well write x to the negative 2, and then we're going to take the limit as t approaches infinity. What's the antiderivative of x to the negative 2? It's x to the negative 1 divided by negative 1. And you can leave the negative 1 in here, or you can bring it outside, and you can even bring it outside of the limits. Because remember, limits are still our friends. So if we continue on, we get minus the limit as t approaches infinity, and then we get 1 over t minus 1 over 1. Well, as t approaches infinity, 1 over t is going to approach 0. So you get minus a 0 minus 1, or 1. So interesting enough, we went from an infinite amount of area under the pink curve to under the blue curve from 1 to infinity. We only have one square unit, the same as the amount of area here. It may be a little bit counterintuitive to you. The best way I can explain that is adding up an infinite number of things could go to infinity, or it could just go to some small number like that. For instance, what if you add up 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, and you keep going forever? Well, 1 is a number, 1/2 is a number, and if you take 1/3 plus 1/4, since 1/4 plus 1/4 would be a half, we could see that this is greater than a half. If we take 2 of these and put them together, and you can keep doing this. If you take the next 4 things and put them together, this is going to be bigger than 4/8, which is bigger than a half. And the next one, if you take the next 8 things, all these 8 things are going to be bigger than 1/16, so when you add them up, they're going to be bigger than a half. So you can see you can keep doubling the number of numbers you take when you're adding, and you keep getting these groups that are greater than a half. So you can see that that's going to go to infinity. Now, if I just took 1 plus a half plus a fourth plus an eighth and kept adding all those up, well, this is 1, say, then this would be a half, and this would be a fourth, and this would be an eighth, and this would be a 16th. I think if you see, if you keep going, you're only going to get 1 more. So this whole thing is only going to approach an answer of 2. So adding up an infinite number of things, it depends on how small they are, whether they accumulate fast enough that you get an infinite amount, or they don't accumulate enough fast enough and you can have a very finite number. Okay, well, what about if we took 1 over the square root of x, this green curve? I think you can see from the picture that it's going to be infinite again, but let's try it just to make sure. Let's take the limit as t approaches infinity from 1 to t. In other words, I know I'm going to do that, and now we have 1 over the square root of x, which is x to the negative 1/2. The antiderivative of x to the negative 1/2 is x to the 1/2, and then you're dividing by 1/2 or multiplying by 2, which you could bring right out front from 1 to t. And then you get the square root of t minus the square root of 1. Well, as t approaches infinity, the square root of t is going to approach infinity again. If you want to go there, almost a bigger infinity here, because the natural log of t is approaching infinity at a slower rate than the square root of t. Okay, so we could go on to 1 over x cubed, 1 over x to the 4th. What about in general if we wanted to take the area between 1 and infinity over 1 over x to the p? So this is going to be a little bit tougher, but we can still do it the same way. We take the limit as t approaches infinity, and this is going to be x to the negative p. So if I take the antiderivative I'm going to get x to the negative p plus 1. And then I have to divide by 1 minus p. And I can bring that right out front. So I get 1 over 1 minus p, and then I have t to the 1 minus p minus 1 to any power is just 1. Now this is where we have to think a little bit more careful. So if I take the limit as t approaches infinity, if t is approaching infinity, if you take it to a power, as long as that power is positive, it's going to go to infinity. So that means the answer to the integral is it's going to diverge if this is positive. Well, it's going to be positive if p is less than 1. Now, if p is greater than 1, that's going to be a negative power, which means if you take something that gets infinitely large to a negative power, it's 1 over that huge number. So it's going to go to 0. So if it goes to 0, you're going to get 0 minus 1 times 1 over 1 minus p, or 1 over p minus 1, if p is greater than 1. And we've already done the case when p equals 1, and we know that it diverges. So I can add that. And now I've taken care of all the cases. So right now, I can say the integral from 1 to infinity of 1 over x to the 10th. We've got a formula now. We don't have to do this again. We know the answer since 10 is greater than 1, we know the answer is going to be 1 over 10 minus 1, or 1/9. So it kind of gives you an idea what you can do with improper integrals when one of these a and b goes to infinity. Now, the other thing that would make something improper is if f of x is not continuous. So what if we were trying to find the area between 0 and 1 under 1 over x? So all this area under this pink curve between 0 and 1, the answer would be the integral from 0 to 1 of 1 over x dx. But that's improper because this function is not continuous at 0. So what I have to do is I have to make the integral from t to 1 of 1 over x dx. And then I take the limit, not as t approaches infinity, we have t approaching 0. And it only can approach it from the right. If we're going in this direction from 0 to 1, we're never going to get to negative numbers. So if we carry this out, we get the limit as t approaches 0 from the right, and this is still the natural log of x. We still don't need the absolute value from t to 1. So we get the natural log of 1 minus, which is 0, minus the natural log of t. Well, if we think of the natural log function as you're approaching 0, the natural log is approaching negative infinity. So you get a minus negative infinity or infinity. So again, that integral diverges, and we know that the area in here is also an infinite amount of area. Now, let's try to do it with 1 over x squared, this blue curve. So I'll just make it x to the negative 2 dx. Again, you're going to have to do the same thing and make it from t to 1 of x to the negative 2 dx. So you get the limit as t approaches 0 from the right, and the antiderivative of that is x to the negative 1 divided by negative 1. So again, we could bring that all the way out, and you're going from t to 1. So you get 1 over 1 minus 1 over t. Well, as t approaches 0, 1 over t is going to get huge. So you have minus this negative infinity. Again, it's going to be an infinite amount of area. So there was a very finite amount of area this direction, but you can see 1 over x squared works more like 1 over x when you go in the other direction. And I think we've probably done enough of these. I think you could find out pretty easily if you went 1 over the square root of x dx. Well, I think we should carry it out. What do you think the area is going to be over 1 over the square root of x, this green one? Guess in your head what you think that area is going to be, and then we'll work it out. So to do this, we have to make it proper. We take the limit as t approaches 0 from the right, and this is x to the negative 1/2. So the antiderivative is x to the 1/2 divided by 1/2, or times 2, which I can bring right out there, and I'm going from t to 1. From the right, so I get the square root of 1 minus the square root of t. Now as t approaches 0, the square root of t is going to approach 0. So you just get 2 times 1, or 2. Now, could we have guessed that? Yes. This green curve right in here is just like the blue curve was when we went in this direction. So this area in here, which we found to be 1, is going to be the same as this area up here, but then we've also got this square right here. So it does make some sense. Okay, lastly, let's just try something. Let's take this area right here under the pink curve, under 1 over x, which we found out to be infinite. So we have an infinite amount of area. Let's take that and revolve it around the x-axis. And what are we going to form when we revolve it around the x-axis? We're going to get this infinitely long horn. And I wonder what the volume inside that horn is. So we're going to go by discs, because we're going to make a little rectangle and do discs. Pi times the integral from 1 to infinity, and we're going of the radius squared. Well, the radius is just 1 over x. So we've already done this problem. This is just 1 over x squared, and we already found that the area was 1. So that means this whole integral is going to turn out to be 1. The whole volume is equal to pi. So it's kind of an interesting thing. We take this infinite area and revolve it around the axis and form a volume of this horn, which is very finite. This is a paradox. And this horn has become very famous. It's called Gabrielle's horn, named after the archangel in the Bible who was dealing with connecting the finite world to the infinite world. And it's also called Torricelli's trumpet, after the famous Italian mathematician Evangelista Torricelli, who actually was doing his studying of this very idea before Newton and Leibniz were formulating their ideas of calculus. So he was somewhat hindered in what he could do, but he was famous for many other things. So they named this after him. Anyway, there's a lot of things. I think I've gone into it far enough for this lecture, but if you want to go on the internet and look into this, just type in Gabrielle's horn, Torricelli's trumpet, or you could type in the painter's paradox, because the paradox is you could have a finite amount of paint, the volume, to paint an infinite amount of surface area. Even though we just looked at the area in 2 dimensions, if you do the calculus and find the surface area, you find out that it is an infinite amount of surface area. So it's a very interesting problem. It's a paradox. Those are always interesting. Okay, so let's get into the types of problems you're probably going to see. So I have 4 of them here. Find the area in the first quadrant between this function and the x-axis. So that's implying that it goes on for as long as you want in the x direction. So if you look at this function, if you put in 0, you get 1 over 2. So it starts out here, and I think if you graph it, it goes like this. So yes, these terms keep getting smaller, but we would like to know what that area is in there. So what we're going to do is we're going to take the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. But that's improper. So what we have to do is take the limit as t approaches infinity, the integral from 0 to t. Now we still have to be able to take integrals. So if you really think about it, if you let u be e to the x, what I have here is 1 plus u squared. And du is e to the x dx. So what we have is du over 1 plus u squared. Well, that's the form of the inverse tangent. So what we get is the inverse tangent of u from 0 to t. So we get the inverse tangent of e to the t minus the inverse tangent of e to the 0, which is 1. So what we have to think about, e to the t is going to go to infinity. And what's the angle whose tangent is infinite? Well, if we think of the tangent curve, it goes like this. So the angle would be at pi over 2, and the angle whose tangent is 1 is pi over 4. So altogether, the area under this curve to the x-axis is pi over 4 square units, a little bit less than 1 square unit. So a little bit less than you'd find in that square right there. Okay, so now find the area in the fourth quadrant between the natural log of x and the x and y axes. So we're going to find this area. So in order to do that, we're going to make our rectangle dx, and you're going to take the area to be the integral from 0 to 1, and be careful, what is that height? Since it's negative, it's going to be minus the natural log of x, and the width is dx. And you could take that minus sign up front, and we could make this proper. It's improper now because the natural log of 0 does not exist. So what we have to do is make it minus the limit as t approaches 0 from the right again of the integral from t to 1 of the natural log of x dx. Well, if you remember back when we did integration by parts, we had to do this by letting u equals the natural log of x and dv being 1 dx. And we found that the answer to this is x natural log of x minus x. So we get minus the limit as t approaches 0 from the right. Now if we plug in 1, we get the natural log of 1 is 0. And if we plug in t, we get t natural log of t minus t. So we have another problem here. What is the limit as t approaches 0 of t times the natural log of t? Because t is approaching 0, and the natural log of t is approaching negative infinity. So we have this indeterminate thing when you multiply one number that's getting close to 0 and the other number that's getting close to infinity. We have to change it into the limit as t approaches 0, and then we would make it, instead of t times the natural log of t, the natural log of t divided by 1 over t. And now they're both approaching a form of infinity. So we yell, L'Hopital! And we can say the limit as t approaches 0, and we take the derivative. 1 over t divided by negative 1 over t squared. So we get the limit as t approaches 0 of minus t. So, yes, this does go to 0, and t goes to 0. So the only thing left is this minus 1 times minus 1, or 1. So that was quite a bit of work. It was a lot of fun, and we found out the area between the natural log of x and the y-axis. This is the same as 1 square unit. Okay, so find the area between 1 over x cubed and the x-axis between negative 1 and 3. So you can see the problem. At x equals 0, which is between negative 1 and 3, we've got a discontinuity in this function. There's an asymptote here. So we're trying to find this area plus this area, which could be finite or could be infinite. Depends on how fast it's hugging the y-axis. Well, just to show you something, let's take and see what would happen if we took the integral from negative 1 to 3 of 1 over x cubed dx. Then you would get x to the negative 2 divided by negative 2. And we go from negative 1 to 3. And you can see we get a very finite number. I won't even bother continuing on. You can see if you plug in 3 and negative 1, you're going to get an answer. unfortunately, that's not the correct answer. We use the fundamental theorem of calculus on an improper integral, so we can't count on that as being right. And I'm just going to show you something. What if we just took from 0 to 3 of x to the negative 3 dx? Again, that's improper because of the 0, so we could make this t and take the limit as t approaches 0 from the right. So we're just looking at this one area over here. Well, again, you're going to get the limit as t approaches 0. The antiderivative of x to the negative 3 is x to the negative 2 divided by negative 2. You put that out front. The limit as t approaches 0, and you get 1 over 9 minus 1 over t. Well, 1 over 9 is a number, but as t approaches 0, that's going to approach infinity. This 1 over t is going to approach infinity. So minus a negative infinity, this is going to go to infinity. It diverges. We're saying that just in this little section, there's an infinite amount of area. So obviously, this is not right. You could say that the area between the curve and the x-axis diverges to infinity. So be careful. It would be very easy to forget about this continuity at 0 and just use the fundamental theorem of calculus, and you could see you'd get a mistake. Okay, so instead of going between a curve and the axis, I thought I would do one between two curves that both are looking kind of similar. E to the minus x and 1 over x squared. So, and we're going to go to the right of x equals 1. So 1 over x squared starts at 1 and goes down like that, and it has a horizontal asymptote, the x-axis. E to the minus x starts out at 1 over e and does that. So we're trying to find the area in between that. So now our rectangle goes like that. So we want to take the integral from 1 to infinity, and the height of that rectangle is going to be 1 over x squared minus e to the minus x, and the width is dx. So the first thing you're going to do is make it proper. You can take the limit as t approaches infinity, and you're going to take the integral from 1 to t. I'll write it right out. So you get x to the negative 2 minus e to the minus x dx. So what is the antiderivative of x to the negative 2? It's x to the negative 1 divided by negative 1 minus, and the antiderivative of e to the minus x is minus e to the minus x. So this becomes plus e to the minus x, and you're going from 1 to t. So if you plug in that, you get minus 1 over t plus e to the minus t when you plug in t, and then if you plug in 1, you get minus 1 and then plus e to the minus 1. Now as t approaches infinity, that's going to go to 0, and that's going to go to 0. So the answer is just going to be 1 minus 1 over e. A pretty small area. If you think of e to be in about between 1/2 and 1/3, that this is less than 1 square unit. The area in between here, all the way out to infinity, is less than this. So I think whenever you're talking about infinity, this just gets exciting, and it also deals with asymptotes. This has been fairly long, so I don't want to do any more, but if you've got the time, just take the tangent of x between 0 and pi over 2 and see if the area between the tangent of x and the x-axis between 0 and pi over 2 is finite or infinite. So it depends on how fast the tangent of x is approaching that asymptote at x equals pi over 2. So, thank you for listening.